is how to calculate, given a function, how to calculate its Fourier series approximation. Yeah. The function. So what kind of function we use here? We know it's a periodic function first. Second, regarding the discontinuities, the number of discontinuities in the function, finite number of discontinuities in each period. So here we're talking about one period, okay? Yeah. Because as a periodic function, you repeat that period, on the whole real axis. Then, if you look at the total number of discontinuities, infinite many number of discontinuities, yeah, but in one period, we assume our assumption, finite many discontinuities. Yeah. Yeah. Because if there are infinite many, so then it could be very complicated. So our discussion, will be very messy. Yeah. To avoid that. Yeah. So here we avoid that, messy part. But in our real world applications, yeah, so this assumption is very reasonable. Yeah. In the real world. Yeah. So almost all the questions, the functions we study here, yeah, can cover, may not be 100%, but close to 100%. Yeah. So don't worry about that. Yeah. All right. Part B. So now we need to go to another level higher, Fourier integrals. Yeah. So now we need to study. We need to take integrals. Yeah. All right. And we need to study the properties related to the integrals. We know the Fourier coefficients we calculate using integrals, right? Yeah. But we want to see if we use the Fourier series, or because the Fourier series is infinite series, right? Infinite series. Yeah. But in our real world applications, we cannot use infinite series, right? In our real world applications, we have to take finite many terms of the infinite series to do the calculation. Yeah. But the question is, if we only take finite many terms in the infinite series, how good is the approximation? Now, we want to study how good is the approximation. If the approximation is very bad, then it could be a problem. Yeah. All right, so let's study the approximation. Yeah. So the first part a little bit theoretical, yeah, but we have to go through this approximation stage. Yeah. The theory part. All right. Approximate a function by partial sum. We have seen this partial sum approach. Yeah. In our power series, we use the partial sum to study the convergence of the power series. Yeah. All right. Here, we use partial sum again, but this time we do not use the partial sum to study convergence. Yeah. In our part way, we already passed that convergence stage. Yeah. But in our part B, we want to use partial sum to study the approximation error. Because when you do approximation, you have some error. Yeah. The question is, how large is your approximation error? We want to control. Yeah. So we want to put the approximation error under control. Yeah. All right. So, but if you use the infinite series directly, you need to work on infinite many terms, right? Yeah. So that could be hard. Yeah. That could be hard. Infinite many terms, hard to control. Yeah. So how to make it easier to control? So we take partial sum, then Yeah, finely many terms. Yeah, so we do not need to worry about the convergence, right? Yeah. So we have the formula covering all the terms. That's easy to handle. Yeah. All right, so let's start. But before we do our work, we need to first, we need to do our preparation. Yeah. First, so Josh just joined us, but I need to do it here. Yeah. Yeah. Otherwise, I have some technical problem. Yeah. All right. First, look at our function. Yeah. So this function is a simple function. Yeah. Oh, pick a time. Yeah. Remind me tomorrow. Yeah. Let me say this. Remind me tomorrow. Yeah. Yeah. Oh. Yeah. Oh. Let's pick a time. Yeah. Pick time because I need to select time. Yeah. That's bad. Let me select a very late time. Yeah. It's quite annoying. Yeah. Every time I need to do this. Yeah. All right. Yeah. So use this function as an example. Yeah. Yeah. But we need to, when we work, we need to consider a general function. Yeah. All right. Yeah. Next, yeah, causing the problem because that interruption, disable my PowerPoint slides. Oh, yeah, I got frozen. Yeah, my screen frozen. So let me kill the program. That's yeah. The good thing is we just get started. Yeah. No big loss. All right, so PowerPoint PPT. Yeah. PPT, I need to, stop. Let me see. End the task, PPT, right? Yeah. End the task. Yeah. Kill it, okay? Yeah. And then restart it. Yeah. All right. Yeah. Okay. Yeah. So we can't. Yeah. This slide. Yeah. All right. Play again. Yeah. All right. Change my pen color. All right. Yeah. Let's continue. All right. There. Yeah, so here, I just recall. Remember last time we did approximation in this way. Yeah, so let's recall a little bit. Because last time we calculated the Fourier series for this function. Yeah. Yeah. We can call it step function. Yeah, so here it's a periodic rectangular wave. Then we calculate, we use the partial sum to look at the approximation, the first three partial sums. The first one term partial sum, that approximation is like this. Pretty bad, but you can see, some approximation. Yeah. The second, better, yeah, approximation is a little better. Closer, yeah, the shape, yeah, yeah. And the third one, even better, yeah, becomes better and better. Now you can imagine when we add more and more terms in our partial sum, more and more terms. 100 terms, can you imagine? If we use 100 terms, you can see the shape should be very close. Very, very close. Yeah. Then 1,000 terms, how about that? Yeah. Extremely close, right? Yeah. But here, this is the visual effect, right? Yeah. But we want to use our formula to do the calculation, can we see how large is the error term, the total error term, when we increase the number of terms in our partial sum? So then we have the confidence. When we do the approximation, we know we can always get excellent approximation. And we have computers. We can use our computers, we can write programs, calculate the partial sum to approximate the original function. All right? So here, we studied approximation, so we need to, select our function first. F of x on the interval, from negative pi to pi, this interval, that can be represented on this interval by a Fourier series. Okay. All right. With this assumption, we need to the first thing is, what is the error? How do you define error? Although we know the meaning of the word error, right? But in math, do you know how to define this error, the quantity of this error? When you approximate, here you use Fourier series. You use the partial sum of the Fourier series to approximate original function. The question, how do you define the error term? Error, the total error. So we need to answer that question first. Consider the nth partial sum. So that's the function we use to approximate original function. Nth partial sum. Definition is like this. Okay. A0, A coefficients, B coefficients, we know how to calculate, right? So last time we have the formulas. The integral formulas to calculate A coefficients, B coefficients. So here we have no problem. We just use those coefficients here. Then we can write this function out, right? This right-hand side function, the finite sum function. This function is well defined, no problem. Very nice function. Okay, all right. The question, you have the right-hand side function, left-hand side function is the original function. There is a difference. You can calculate the difference. The question, do you want to use the difference to define the error part? Here, our first question. We want to figure out what is the best way to describe the error, right? Here you can imagine there are many different ways to describe errors. Not a unique way. So it's not a unique way. There are many different ways to define errors. So which one is the best? Here I want to answer this question. Which way to define the error is the best? How good is the approximation? First, let's draw the graph and get some understanding from this graph. All right. Select an arbitrary positive integer n and fix it. All right. So the right-hand side function is a fixed, nice function. Okay. All right. Consider the all trigonometric polynomial. Here we use another concept. Here we use this concept. Trigonometric polynomials. We know polynomials, right? Algebraic polynomials. We're familiar with algebraic polynomial. Here, trigonometric polynomial. That term, okay? What's the trigonometric polynomials? This expression we called trigonometric polynomial of degree n. That expression, that's what we call a trigonometric polynomials. do you know why we can call this structure trigonometric polynomials? Yeah. Yeah. If you want to connect this function to polynomial function, yeah. So because when you see this word, you may not be able to see the connection of this expression to polynomial, right? Yeah, yeah. So actually, there is some connection, yeah. Because if let's consider the polynomial function a0 plus a1x plus dot 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 plus a n times x to n. That's the standard polynomial, right? Yeah. All right. But in this polynomial, now we consider the special case. X is the e function. Okay? E function. E to the I x, you know, square root of -1. All right? That constant. Yeah. You know. Yeah. Complex numbers. If when x takes e to the I, let's say t, yeah, because you cannot use x anymore, right? I times t. Then you plug in, yeah, so you can see this time your polynomial becomes p of t. Yeah, this time it's a t variable, right? Yeah, a0 plus a1 e to the it, right? Plus a2 times e to the 2it, and so on. The last term, an e to the nit, right? Yeah. Then by Euler formula, so you know Euler formula, right? Yeah. So the e function, e to the, let me use nit cosine of nt plus I times sine nt. Okay, so you have the cosine and the sine, right? If you write it out, although not exactly the same, but you know, a lot of similarity, right? Yeah. So in this way, so that's why, you know, mathematician, you know, so they make this terminology trigonometric polynomials. Okay? Yeah. Yeah. All right. Some connection. Yeah. All right. Yeah. So now we want to study all the trigonometric polynomials of degree n. Yeah. Can we study the whole class of these functions? Yeah. Or you can also use the set concept, the set of function. Yeah. The class or set, you know. Yeah. Yeah. No big difference. Set. Yeah. The whole. We put all the functions in this form in one set, and we study this set of functions. Okay, all right. Then, this time we define one, yeah, so this capital F function, one capital function. This is a representative from a set, okay? Yeah, so here I'm talking about this circle represents the set of the functions of degree n trig polynomial. Okay? Function. Okay? Yeah. Yeah. Then, in this set, we select a representative. Okay? Arbitrary one from this set. And we choose it as a representative of the function in this set. This capital F is that representative. Okay? Yeah. Then constant term, capital, we use capital A0 versus lowercase a0, because lowercase, we mean Fourier coefficient, right? Yeah. Capital A0, arbitrary coefficient, okay? Nothing to do with Fourier coefficients. So you know the difference, yeah. Similarly, capital A and capital B and arbitrary coefficients, okay? All right, yeah. So then, now we want to study, yeah, with this capital F function, how close this capital, yeah, because we want to approximate our original function. Use a function from the set. How about that? Can you see? Yeah. In this set of functions, there are large number of, yeah, so here I need to mute it. Mute it. All right. Large number of functions. The reason we study this set of functions, we want to pick which function in this set has the best approximation to our original f function, right? That's the reason. Why you study the whole set? Because this whole set gives us a lot of freedom to choose trigonometric polynomial from this whole set, right? We have freedom to choose. Okay. We have freedom to choose. Do you want to choose the best one? The one that approximates the original function f the best, right? Yeah, we want to find the best approximation from this whole set. Okay, yeah. So that's the reason. Yeah, we study. All right. So now we want to do the calculation. Yeah, based on this understanding, we want to do the calculation. Yeah. All right. Yeah, so the question, we want to answer this question. Next question. Which one in the set, okay, which one in the set has the best approximation? All right, we'll need to answer. The goal of our, yeah, I will add it. The meaning, first we need to, yeah, I mentioned this question before, but here we need to answer it. Yeah. The meaning of the best approximation. Yeah. Because we haven't defined the error, right? What's the error? We haven't defined it. Yeah. So this is orthogonality. So we will get this orthogonality quickly. Yeah. All right. So here, the first thing we need to define appropriate error. Yeah. There are so many different ways. Which way is appropriate? Here, this word pretty vague, appropriate, but I will explain. Under what senses? Yeah. Under some special sense, then we can say appropriate or not. Yeah. All right. Yeah. So this is the Fourier series approximation. Yeah. So this one is the Fourier partial sum of the Fourier series. Yeah. Partial sum. Yeah. Okay. Yeah. All right. Then this is the representative of the trigonometric polynomial, right? Degree n. Representative. So they are different. The meaning is different. Yeah. Although they are correlated. Later you will see they are correlated. Yeah. Here, the meaning. Yeah. Do not get confused. Okay. These two expressions. Yeah. All right. Here, best means that the error, yeah, this error, we haven't specified the meaning of the error. The error of the approximation is as small as possible. Now, let's fix the error definition. What is the definition of this error? Yeah. All right. When we start, let's look at our intuitive. First, based on our intuition, what is the error? Take the difference, right? Yeah. Take the difference. Yeah. Then, negative, positive, we'll only consider the non-absolute value, right? Because when we talk about error, so we don't look at a sign, positive, negative. We look at absolute value. So we need to take the absolute value on the difference. Yeah. All right. Little f function minus capital F function, yeah, take absolute value, but because the difference at different x point, the error number is different. So which error number you want to use? Yeah. Here we take the maximum value of the error number in this interval. That's our first try. Okay? Yeah. When we talk about, that's our first natural try, right? Yeah, because most people will use this way. Yeah, at the beginning. Yeah. But next question, is this a good way to define the error? Yeah. So this is one of the many ways, but is this a good way? Yeah. All right. So here, let me draw the graph. Yeah. So from the graph, we want to see if it's a good or not. All right. Look from this graph. Okay. Yeah. The solid line, yeah, that part, solid line, that corresponds to the little f function. Yeah. Because in our assumption, our f function can contain certain number of discontinuities, right? Yeah. Yeah. Because in our real world, discontinuity. Oh. Yeah. Discontinuities. Nuities. All right? Yeah. Here, this pair, we only consider one discontinuity. Okay? At x0, discontinued. All right. At a discontinuity point, we want to see how good is the approximation at a discontinuity. Yeah. Because this f function, it's a trigonometric polynomial. It is always continuous, right? It's a smooth. Yeah. It's a nice smooth function. Yeah. So this dotted curve, yeah, that's the smooth curve. Yeah, very nice smooth curve. Now you need to use a nice smooth curve to approximate a function with discontinuities. Yeah. How good can you approximate at each discontinuity point? How good? That's the question. Okay? That's the question. Yeah. All right. So think about it. Yeah. So here, in order to let you see how good it is, yeah, can we imagine the jump? Yeah, jump. So there is a number difference at this jump, right? Yeah. Remember last time we used the left limit. So you calculate the left limit number and the right limit number, right limit. Okay? Yeah. You calculate the difference of the left limit, right limit. Yeah. That's the jump number, right? Yeah. So that jump number here, let us assume, for simplicity, let us assume that jump equals 1. How about that? 1 difference. All right. At that point, x0, yeah, that jump is 0. Jump is 1. If you use this way to calculate error, how well it is, how good it is. Okay? Yeah. Yeah, because this is a continuous function. Yeah. So when you calculate so here we calculated this number from two sides, left limit, right limit, two sides. How about that? Okay? From left limit, let's calculate x0 from the minus direction. Then the second time we calculated the limit x0 from plus direction, right limit, right? Left limit, right limit, okay? All right. And the difference of left limit and right limit of this little f function is 1, but for this capital F function, left limit, right limit the same, right? It's continuous. Continuous left limit, right limit the same, all right? So how can you use the same capital F value to approximate two different left limit, right limit, two numbers. That number is what? That is what? So the difference, is it the difference is at least 0.5? That means you cannot approximate the original value better than 0.5. Okay? Yeah. Difference is what? If you're close to the higher value, then the difference between F, capital F, and the lower value will be larger than 0.5. If you're close to the lower one, then the difference of the capital F value with the higher one will be greater than 0.5. You can never do better than 0.5. Think about that. Then, this error definition, you can never make it as small, sufficiently small. Yeah, because 0. This fixed number, you cannot never do better than this 0.5. It's very bad, right? Yeah, because in our approximation, if we can never do better than 0.5, 0.5 is just this example, right? Yeah. If some example the gap is 100, you can never do better than 50. That's horrible. Yeah. If you do this in the real world applications, you can never do better to make the difference smaller than 50. That's too bad. Yeah. So for that reason, so we feel this definition of the error not appropriate. It's a bad definition. We cannot use it. Okay? We cannot use it. We have to choose a different definition such that we can make our error part as small as possible. If we want to make it smaller than 0.1, we can make it. If we want to make it smaller than 0.00001, we can get it. That's a good definition of error, right? Yeah. So the second one, the better one, define error. Integral on the whole interval from negative pi to pi, then we take the square of the difference on this interval. Square difference integral to define this error term. Yeah. Then this one is much better. Yeah. Let me explain why this new definition is much better than the first one. First, this one, in this example, we can see when we take more and more terms, we can make this integral smaller and smaller, very close to 0. So why? Because remember, the meaning of integral, what's the meaning of integral? Calculating the area, right? Integral, when we calculate integral, basically we calculate the area, okay? All right. Now, look at the area difference. Area difference. The area for this part could be very close to 0. We don't worry, right? Mainly we worry about the area difference in this part, around the discontinuity point. Yeah. But in this way, a continuous function, you can make it very close. The error becomes smaller, smaller, smaller. Okay? Yeah. Even if the error, yeah, because we worry about the gap, 100, 50, 100, that gap's still there. Okay? That gap is still there. Let's say the gap part is 100. But we can make the difference part within the skinny rectangle, right? So that the difference part is, we can control, put it in a very skinny rectangle. Can we make this rectangle more and more skinny? More and more skinny? If the more and more skinny, the error close to 0, right? Yeah. So if you want to control the error smaller, smaller, we shrink. Okay. Yeah. We make the area close to 0. Then we can get any good approximation. The approximation with any precision you want. So then it's a much better one. Okay? Much better one. Yeah. So that's the first. And this is the most first and most important reason we choose a different error definition. Yeah. But there is another one, also very important. Yeah. Second important. That is when we do math calculation. Yeah. The formula, we need to do calculation, math calculation. If we work on the absolute value, it's very hard to work. Yeah. Okay. It's hard to take derivative. It's hard to take integral, because integral you need to consider, positive, negative, right? Very messy. Yeah. When you take integral on absolute value expression, yeah. But think about when we take integral on the square, we can expand square. Yeah. Normal integration, yeah, much easier. So from the calculation point of view, yeah, the second term much better. Yeah. We can do, we have a lot of freedom. Or we have, we can do much better. Yeah, yeah. All right, yeah. No discussion, positive, negative discussion. Yeah. All right. Yeah. Square error of capital F. Yeah. Capital F, we have freedom to choose what capital F. Yeah. So every time when we choose F, we can calculate this error term. Yeah. Now we go back to the set trigger polynomial degree n. Okay. Yeah. Now, can we search the whole set, and we want to find the one that has the best approximation to this original f function? How about that? Yeah. In that set, yeah. Which one? Which capital F? Capital F, that means we need to find all the coefficients, capital A, capital B coefficients. Find all of them. Determine those capital A, capital B coefficients such that the corresponding capital F function has the best approximation to the original little f function. That's the question. We need to answer that question. Okay, all right, yeah. Estimate the error. Now we need to do the calculation. Calculate, error. Yeah. Square, we expand the terms. Square formula. Yeah. Then we take integral, one by one. Yeah. Yeah. We need to do a lot of calculation, but not too hard. We can handle. Okay, all right. But when we do the calculation, so here, can you see after expansion, we need to calculate these three integrals. Yeah. So this one, because can we write f squared minus 2f capital F plus capital F squared? Okay. The first one, we have the first integral. Yeah. Second one, we take the constant 2 out, second integral, minus, and the third one. Yeah. We want to calculate these three integrals one by one. Okay, all right. Yeah. The first one, we keep it. First one, we do not need to calculate. Yeah. First one, f squared. Yeah. Whatever that function is, yeah. If the little f function is given, this integral is given. So we have nothing to do, right? Yeah. Yeah. But the second integral, the third integral, because we have, we can do calculation. Okay, all right, yeah. When we do the calculation, one important tool, because it could be very messy, right? When you do expansion, so many terms, integrals, it could be very, very messy. How to make that calculation part easier? Then remember, these cosine functions, sine functions, remember the last time we said it's a basis function, right? Yeah, basis function. Yeah. Basis function, even better, orthogonal basis. Remember the orthogonality. This orthogonality integral of this 0. Okay, yeah, and the two more, yeah, 3 types integral, orthogonality property, yeah, m and e even, yeah, these 3 integrals are 0. That is the best we can get, because when we do the calculation, a lot of terms 0 gone. Okay, yeah. After that, yeah, after we remove all those 0 terms, the remaining part, very nice. The remaining part, very nice. Yeah. All right. Yeah. So let's look at the minimum square error theorem. Yeah. The result, the final formula of the minimum error calculation theorem. Yeah. All right. Yeah. So when we start, yeah. Now we do the calculation. Yeah. So the error definition like that. Yeah. All right. Yeah. Let's calculate this capital F square calculation. Yeah. We need to take square. Okay. All right. You may get scared to do the calculation of this one, right? Expansion. Yeah. Square. Yeah. But you just think about. Yeah. You have the many square terms. Other than square term, you have the cross terms, right? Many cross terms. The cross terms, integral, all 0, all gone. Okay? Yeah. You only keep the square terms. Yeah. All the cross term by the orthogonality property, all gone. Yeah. You just think about that. Yeah. Yeah. Not that bad. Yeah. So here you can see that we keep all the square terms. So we have all these squares. But the cross term, integral, all 0, so we don't have them. Okay? All disappear. Yeah. So the calculation result is this. Pi times, yeah, because you take integral from negative pi to pi, right? Negative pi to pi, yeah. So constant, so that's why you have this 2 pi. The first term, you have 2 pi, okay? Yeah. Yeah. But after the first term, yeah, the cosine and that one, so you don't have that 2 pi, yeah. So all square. Yeah. Sine square, cosine square, you take integral. Yeah. 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 So use the formula. Yeah. Square, yeah. You have that 1/2 constant out, right? 1/2. Then you do integral from negative pi to pi. 2 pi times 1/2, you get a pi. Okay? That's why for all other terms you only have pi. But for the first term, yeah, it's a constant. Yeah, sorry, not here. The first one, capital A0 square, but you do integral from negative pi to pi. Yeah. So that's why you have 2 pi. Other than that, all other, you don't have 2. Yeah. All right. That's the third integral, capital F square. Then we need to calculate the second integral. Second, little f times capital F. Okay? Little f times capital F. That coefficient 2, we can skip it temporarily. Yeah, that 2. Yeah. So we just calculate integral little f times capital F. Yeah. But the capital F, we use this expression, capital F. Then you take a little f, cosine, sine part, you get a Fourier coefficients, right? Yeah. So you get a Fourier coefficient little a. The little a, little b, okay? All these little a, little b, yeah. Right. Then the original capital A, capital B, also you need to carry those capital A, capital B, yeah. All right? For those cosine square term, sine square term, you have that. For the cross term, all gone, okay? Sine, cosine, but with different m and n, all gone, okay? Yeah, so those part all gone. Yeah. So you only do the same basis function, yeah, cosine square, sine square, that part non-zero, you can calculate. So the result is like this, okay? Yeah. Yeah. Each individual term, capital A and the capital lowercase a, capital B, lowercase b, yeah, like that. All right? Yeah. Then put together. Yeah. Yeah. Because we have three integrals. So the first integral, we do not need to touch it. First integral, little f, whatever it is, yeah, leave there. Yeah. So then the second interval and the third interval. Yeah. All right. Then what is this e? Our goal, we calculate that e. Yeah. All right. We put them together. So this e, these three integrals. Yeah. Keep the first one. The second one, third one. Yeah. Remember, yeah. Second one, third one. Yeah. We can rewrite it. So this is algebraic. Yeah. Can you imagine after we, yeah, so here, yeah, 2 pi, rewrite it. Yeah. Yeah, so get that, yeah, all right, yeah, so you can check it, all right, check it, yeah, 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 because here, minus, plus, right, minus, this part is plus, yeah, all right, now, yeah, you multiply 2, yeah, oh, yeah, so let's see, yeah, there is a, right, this part, the plus part, okay, yeah, all right, yeah, right, yeah, so that's exactly that one, right, yeah, yeah, the summation way, that's exactly that one, right, yeah, good, yeah. Can you simplify it? The question. Yeah. Can you simplify it with this structure? Yeah. All right. So let's look at the simplification. Yeah. So here. Yeah. All right. Let's consider. Yeah. Let's consider this is the general case, right? The f. For any capital F, we have this expression. All right. Now, can we choose f? Can we choose one special f? Yeah, so here, I may like to, yeah, because we use star. How about we choose f, capital F star of x equals this expression? How about that? That is the partial sum of the Fourier series. We here, because we have freedom to choose all possible capital F, can we consider a special f? We call it f star. That f star takes this partial sum for it. That f star, if we calculate this e on that capital F star, we have this e star error. Yeah, this is a special case of the error, so we use the star. Yeah. How do you get star? Yeah. Our capital, we make capital A 0 equals little a 0. Capital A sub n equals little a sub n. Capital B sub n equals little b sub n. We choose the special, capital A, capital B. When we choose that, lot of cancellation here, right? Yeah. Lot of cancellation here, yeah? Right? After cancellation, simplification, we have this expression. Yeah. We have that expression. Okay? Yeah. E star error. E star error. Okay? All right. The next question. Yeah. So here, we're closer to our destination. Our destination, we want to show this E star is the best error, okay? Better than any other. Better than any general. Okay? Yeah. The next question, how can we see this E star give us the smallest possible error E. This special E star gives us the smallest possible error, capital E. Next, we need to see that. Yeah, that's this theorem. Okay, this is important theorem, minimum square error theorem. Okay, all right. Yeah. To see that, we need to compare capital E and capital E star. Yeah, because here we have these two expressions explicitly. We have both. Can we use the capital E minus capital E star, takes subtraction? Yeah. If we take that, the first term cancel out, right? Yeah. Little f squared, they both have this little f squared integral. Yeah. The first term, unknown, but cancel out. Okay. Then the remaining terms, can we do cancellation, combination, then complete square thing. That the remaining one, after we do some simplification, we get this expression. Very nice. We get this expression. This expression. First, can you see, because this expression greater or equal to 0, can you see that? Yeah. Because in this expression, little a, little b, all fixed. The Fourier coefficients all fixed. Capital A, capital B, you can change. You have freedom to choose different capital A. Whatever you, capital A, capital B, you choose, the difference, this expression, always non-negative, right? Always non-negative. But when you choose capital A0 equals little a0, the capital A equals little a and capital B n equals. When you choose that, you get the smallest difference number, right? Smallest difference number, okay? That means your error is the smallest. Yeah. Your error is the smallest. Yeah. Capital E, always greater or equal to capital E star, then capital E star is the smallest. That obvious. That obvious. Yeah. That means, what's the conclusion? Yeah. All right, let's take a break. Yeah, because this part, the conclusion part. Yeah. So when you come back after the break, so let me just, clean up, summarize. Yeah. Then we make the conclusion.